Hello everyone. Today my chapter is Chemistry of Lanthanide Elements. We have learned that the elements in which the last electron enters the f orbital of their atoms are called f block elements. In these elements, the last electron is added to the third to the outermost called anti-penultimate energy level. Example n-2f. These elements are called inner transition elements because these constitute transition series within transition series d block elements. They consist of two series of elements placed at the bottom of the periodic table. These two series are formed by the filling of electron in 4f and 5f orbital and are called lanthanide and actinide respectively. The series involving the filling of 4f orbital flowing lanthanum. Lanthanum atomic number is 57. Is called lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in this series starting with cerium and ending with lutetium. The name lanthanide is derived from lanthanum, the first member of the series. These lanthanides are also sometimes referred to as lanthanones. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that the 4f orbital in which the electrons are added are embedded in the inner shell, while 5d and 6s electrons which have similar configuration are exposed more to the surroundings. Because of their similar properties, their separation and identification prove to be very difficult task. The first stage in their separation was to get them as oxides. However, the occurrence of the oxide of lanthanide was very rare. Therefore, these elements have been called rare earth elements. Nowadays, the term rare earth is not used. Their substantial deposits occur in Scandinavia, USA, USSR, and India. General characteristics of lanthanide. The important general characteristics of lanthanides are discussed below. First is electronic structure and position in the periodic table. The lanthanide involve the gradual filling of 4f orbital. It may be noted that the energy of d orbital and the next inner shell f orbital are closely similar and therefore the order of filling of 4f orbital in the atom show quite irregularities. At lanthanum, both 5d and 4f orbital become stable due to the increased effective nuclear charge as a result of the poor shielding effect of 6s electron. Therefore, it is observed that at lanthanum the incoming electron enter the 5d orbital and its electronic configuration is lanthanum atomic number is 57. Its electronic configuration Xe5d1 6s2. However, as we move further after lanthanum, the energy of 4f subcell becomes lower than the 5d subcell and therefore the next electron in cerium enter the 4f subcell. The electronic configuration of cerium is equal to Xe4f2 6s2. The filling of 4f orbital continues till we reach terbium, in which the 4f subcell get completely filled. Terbium atom electronic configuration is Xe4f14 6s2. Now, after 6s and 4f subcell have been filled, the next electron goes to 5d subcell. The configuration of lutetium is Xe4f14 5d1 6s2. This constitutes lanthanide. The general configuration of lanthanide may be written as Xe4f0 5d0 6s2. Second is physical properties. The important physical constants of lanthanide are given in table 2. These are discussed below. First is ionization energy. The lanthanide have fairly low ionization energy. The first ionization energy are of the order of 560 kJ per mole and second ionization energy are of the order of 1150 kJ per mole. These values are quite comparable to alkaline earth metal, especially calcium. IE1 is equal to 589 kJ per mole. IE2 is equal to 1145 kJ per mole. Second is melting and boiling point. Lanthanide have fairly high melting and boiling point. However, the melting and boiling point do not show an irregular trend as we move from lanthanum to lutetium in the series. Inspection of table 4.2 shows that europium and terbium have unexpectedly low melting and boiling point. These atoms form europium 2 positive and terbium 2 positive ions and result in weaker metallic bonding because there are less than 3 electrons per atom in the metallic bond. The other lanthanide atom give 3 electrons per atom in the metallic bonds. Therefore, melting and boiling point of europium and terbium are low as compared to the value for the other lanthanide elements. Third is density. The density of lanthanide are low, which range between 6.7 to 9.74 gram per centimeter cube. However, there is no definite trend in the density of lanthanide with increase in atomic number. Europium and terbium have unexpectedly low values. Fourth is heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trend with increase in atomic number. Fifth is electronegativity value. The electronegativity value of lanthanide between 1.0 to 1.115 are quite close to those of alkali and alkaline earth metals. Alkali and alkaline earth metals are s block elements. Therefore, lanthanides are expected to form ionic compounds. Sixth is electropositive character. Because of low ionization energy and electronegativity values, the lanthanides are electropositive like s block elements. Now the oxidation states. The common oxidation state of all the lanthanides is +3. In addition, some lanthanides shows +2 and +4 oxidation state also. These are shown by those elements which by doing so attain the stable F0, F7 and F14 configuration. For example, cerium and terbium exhibit +4 oxidation state. Cerium and terbium attain F0 and F7 configuration respectively when they get +4 oxidation state as shown below. Cerium 4 positive Xe4F0, terbium 4 positive Xe4F7. Europium and terbium exhibit +2 oxidation states. Europium and terbium get F7 and F14 configuration in +2 oxidation state as shown below. Europium Xe4F7 and terbium Xe4F14. La, and Lu exhibit only +3 oxidation state. These elements shows +3 oxidation state only because by losing 3 electrons they acquire stable configuration of empty, half-filled and completely filled 4f subcells. Exceptional example, some other elements shows +2 and +4 oxidation state even though they have electronic configuration other than F0, F7 or F14. For example, Sm and Tm show +2 oxidation state having F6 and F13 electron respectively, in which they have one electron less than half filled or completely filled configuration. Similarly, Pr and D and Dy show +4 oxidation state having F1, F2 and F8 electron configuration. The stability of this unusual oxidation state may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than the +3 state, which is characteristic of this family. The outer electronic configuration of lanthanide in different oxidation states are given in table 3. Fourth is color and spectral properties. The lanthanides are silvery white, but many lanthanides are colored both in the solid state and in the aqueous solution. The color remains same even on the change of anions. Therefore, the colors are characteristic of the lanthanide ion. The color of the ions depend upon the number of unpaired electrons because it has been observed that the ion containing NF electron have almost similar color to those of 14 minus NF electron. The different ions having NF and 14 minus NF have their color are given in table. However, it has been observed that some di and tetrapositive ions having same number of electrons, isoelectronic ions, as tripositive ions do not have same color. For example, Sm2 positive and europium 3 positive have same number of unpaired electrons, but they have different color. Some other examples are given in table. The color of lanthanide ion arises due to the absorption of light from the visible region of the spectrum, resulting in the electronic transition within the 4f level, FF transition. A remarkable characteristic of the spectra of the tripositive lanthanide ion is that the absorption bands are extremely sharp like bands. in ultraviolet, visible, or near infrared vision. Many of these bands are line like and become even narrower as the temperature is lowered. This temperature is in contrast to absorption bands of DD transition, which have broad absorption bands. The bands of lanthanide ion are so sharp that they are useful for characterizing the lanthanide ions. The main reason for very sharp absorption band is that the 4f orbital lie deep in the atom of these elements. Therefore, they are effectively shielding from the surrounding by the overlying 5s and 5p orbitals, and consequently the absorption band lies mainly from the electronic transition within the 4f levels. Thus, the absorption bands show little dependence on the nature of the ligands. In addition to FF transition, sometimes color of lanthanide ion is also attributed to FD transition. The FF absorption transition of lanthanide ion have low intensity because they are not allowed, whereas FD transition are allowed. In contrast to FF transition, the FD transition are allowed and hence show very intensive absorption bands. For example, the FD transition observed for cerium 3 positive and terbium 3 positive are very intense. Fifth is magnetic properties. All the lanthanide ions with the exception of lanthanum, lutetium, cerium and terbium ions are paramagnetic because they contain unpaired electron in their 4f subcell. The ion lanthanum, lutetium, cerium and terbium, which have 4f0 and 4f14 electron configuration, are diamagnetic because they have no unpaired electron. The magnetic properties of the lanthanide are different from those of a transition electron element. As we know, the magnetic moment arises from two types of motion of the electron. The spin moment of electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produces magnetic moment called orbital magnetic moment. The observed magnetic moment of a substance is due to the contribution of both the spin moment and the orbital moment. In the case of transition elements, d block elements, the magnetic moment mainly corresponds to the spin-only magnetic moment. This is due to the fact that d orbitals are not well shielded from the environment and take part in bond formation with the ligands, atom, ion, or molecule. As a result, the d electron of the metal interacts strongly with the ligands surrounding the metal ions. Due to the electric field of the ligands, the orbital motion of the electron gets restricted and thereby the orbital moment of these electrons get coincident. The magnetic moment of d block elements thus arises mainly from the contribution of spin motion of the electron only. The spin only magnetic moment is given by mu spin only is equal to under root m into n plus 2, where m is the number of unpaired electrons. This relationship gives almost correct value of magnetic moment for d block element. However, the above relationship is not valid in the case of f block element. In this element, the 4f orbitals are well shielded from the surrounding by the overlying 5s and 5p subcell. As a result, the electric field of the ligands surrounding the metal ion does not restrict the orbital motion of the electron. Thus, orbital contribution is not coincident. Therefore, the magnetic moment of lanthanide ion is due to the both electron spin and orbital motion of the electron. This may be calculated from the relation mu is equal to under root 4s into s plus 1 plus l into l plus 1, where s is the resultant spin quantum number and l is the resultant orbital moment quantum number. The theoretical and experimentally observed magnetic moment values are given in table. The magnetic moment of lanthanide depend upon the atomic number and the number of unpaired electrons. For the ions lanthanum, gadolinium, lutetium, the magnetic moment corresponds to spin-only values. The magnetic moment of tripositive lanthanide ions are plotted in figure. Lanthanum and lutetium are magnetic, no unpaired electron. It is observed that the value increase up to neodymium and decrease to 1.47 for samarium ions. It increases again and reaching a maximum value for holmium and prosium. Thereafter, it starts decreasing and becomes 0 for lutetium, which is paramagnetic. Sixth is ionic radii and lanthanide contraction. We know that as we move down a group atomic size, covalent or ionic radii normally increase. This is mainly due to the additional cell or electron between the successive period. However, as we move across a period from left to right, atomic size decreases. This is attributed to the increasing effective nuclear charge, as a result of which the outermost cell of electron is attracted more and more. Consequently, the size decreases. For example, the covalent radii of alkali metals increase from Li to Cs and for halogen from F to I. If we consider the ionic radii of lanthanide, we get a very interesting observation. For comparison's sake, we can take the ionic radii of trivalent ion M3 positive, which is more stable. These are shown in figure. It is clear that ionic radii decrease from one element to another in the lanthanide series, but decrease is very small. It has been observed that from cerium to lanthanum, cerium to lutetium, the ionic radii decrease from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in comparison to element of other group and period. Similarly, on moving from cerium to lutetium, the atomic radii also decrease from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small decrease in ionic or atomic size of the lanthanide element with increase in atomic number is called lanthanide contraction. Cause of lanthanide contraction. In lanthanide series, the 4f electrons are being added one at each step as we move from one element to another. The shielding of one f electron by another from the nuclear attraction is quite weak due to the shape of the f orbital. The nuclear charge, however, increases by 1 at each step. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by the 4f electron increase, and this causes a reduction in the size of the atom or ion. The sum of the successive reduction gives the total lanthanide contraction. Consequences of lanthanide contraction. Lanthanide contraction has very significant effect on the relative properties of the element which proceed and which follow the lanthanide in the periodic table. Some important consequences of lanthanide contraction are given below. First is steady decrease in size. There is a regular decrease in the ionic radii of lanthanide. Second is electronegativity. There is slight regular increase in the electronegativity of the trivalent ions. Third is electrode potential value, denoted by E naught. There is a small but smooth increase in standard electrode potential value, E naught for the process. For lanthanum, minus 2.52 V to minus 2.5 V for lutetium. Fourth is resemblance of second and third transition series. The lanthanide contraction affect the chemistry of second and third transition series. As we can see from table, there is a regular increase in size from Sc to La. Similarly, we expect normal increase in size in other groups. However, after lanthanide, the increase in radii from second to third transition series almost vanishes. The pair of elements Zr2, HF, Nb2, Ta, 2 W, etc. possesses almost the same size. The properties of these elements are also very similar. Fifth is similarity among lanthanide. Because of the very small change in size of the lanthanide ion in lanthanide, their chemical properties are similar. Therefore, their separation becomes very difficult. Recently, method based on repeated fractional crystallization or ion exchange technique, which take the advantage of slight difference in their properties like solubility, complex ion formation, hydration, etc., arising from very slight size difference of the trivalent ion have been used. Sixth is basicity difference. Due to lanthanide contraction, the size of the lanthanide ion decrease regularly with increase in atomic number. As a result of decrease in size, their covalent character between lanthanum 3 positive ion and OH negative ion increase, and therefore the basic strength of the hydroxide decrease with increase in atomic number. Thus, LaOH3 is the most basic while LuOH3 is the least basic. The basicity difference in lanthanide are reflected in first increasing tendency to get hydrolyzed. Due to decrease in basic character, there is slight increase in the degree of hydrolysis in solution from lanthanum to lutetium. Example, lanthanum ion are less readily hydrolyzed than lutetium ions. Second is thermal decomposition of oxysalts. More basic oxysalt decompose less readily Example, NaNO3 whole thrice decompose with difficulty is stable, whereas LuNO3 whole thrice is unstable and decomposes readily. Third is solubility of salt. Lanthanide hydroxide precipitate at regularly decreasing pH values from lanthanum to lutetium. Example, LaOH3 at 7.83, GDOH3 at 6.83, and Lu3 positive at 6.30, all from nitrate solution at 20 degrees Celsius. Seventh is size of heavy helium and dimium. Due to lanthanide contraction, the radius of terbium is comparable to heavier lanthanide terbium, holmium, and ermium. Therefore, they occur together in natural minerals. Eighth is reactivity of lanthanide. All the lanthanide are highly electropositive metal and have almost similar chemical reactivity. This is due to the fact that the lanthanide differ only in the number of 4f electrons. Since these electrons are very effectively shielded from interaction with other element by the overlying 5s, 5 and 6s electrons, they show very little difference in the chemical reactivity. Because of their similar chemical reactivity, their separation from one to another is very difficult. The lanthanide are in general more reactive than d block elements. Some of their chemical characteristics are: first, they turn readily on exposure to air. In finely divided state, they all burn in air to form sesquioxide of the formula Ln2O3, where Ln stands for lanthanide except cesium, which gives CaO2. Terbium, however, resists the action of air even at 1000 degrees Celsius due to the formation of a protective coating of its oxide. Second, all react with water slowly in cooled but rapidly on heating, liberating hydrogen and forming LNOH3. All these combine with hydrogen at 200 and to 300 degrees Celsius, giving LNH3. They also combine with halogen, oxygen, and sulfur. They act as strong reducing agent for oxide of other metals. Helium is used as a scavenger of oxygen and sulfur in many metals. They react with nitrogen to form nitride of the formula LNN. Solubility of compound. The fluoride, oxide, hydroxide, carbonate, phosphate, chromates, and oxalate of lanthanide are largely insoluble in water. On the other hand, the halide, other than fluoride, nitrate, acetates, perchlorates, and salt of oxoacid of lanthanide are soluble in water. The solubility behavior of salt of lanthanide follows the pattern of solubility of salt of group second element. However, lanthanide sulfate, unlike the sulfate of group second element, are soluble in water. Tenth is tendency to form complex. Although the lanthanide ions have a high charge +3, yet they have large size of their ions compared with the transition metal. As a result, they have low charge density and therefore they have very less tendency to form complex. Their complex with unidentical legend are very few and form complexes only with fluorine and oxygen donor legend. However, they form complexes with a few chelating legends such as beta diketones, oximes, and ethylene amine tetraacetic acid, EDTA, alpha dipyridyl, and hydroxycarbolic acid, carboxylic acid, such as citric acid. These complexes usually have high and variable coordination number, and water as solvent molecule are often attached to the central metal atom. Beta diketone complexes of europium 3 positive and promidium 3 positive dissolved in organic solvent are used as lanthanide shift reagent in NMR spectroscopy. In contrast to transition element, the coordination number 6 is not very common. Coordination number below 6 is also uncommon and occur only with bulky legends such as 2,6-dimethylphenyl and SIME3 whole twice legend. However, coordination number 7, 8, 9 are common and these give a variety of stereochemistries. For example, a coordination number 4 LNOH2 and 3 positive in aqueous solution are both to be 9 for every lanthanide and 8 for the latter smaller number of the series. However, these ions are highly labile. The smaller terbium ion YB3 positive ion form 7 coordinated complexes and the larger lanthanide 3 positive is 8 coordinated in the LAACAC whole thrice OS2 twice, where ACAC is acetylene acetonate. The structure of these complexes are a capped trigonal prism and a square antiprism as shown in figure. Coordination number 10 and 12 occur with the larger lanthanide and small chelating is legends such as NO3 negative and SO4 2 negative. Tanisha. Thank you.